All right, so who can come up with an algorithm for this question? Can you guys hear me fine? All right, so who can come up with an algorithm for this? Okay, so let's see. So Paul is saying we can sort the list. So we should take the list, take the numbers, take the 500 numbers, and then we can sort the list, and then we can start. Okay, okay, so if the number is greater than half of 19, then we kind of, okay, so essentially we sort and then we kind of search. Okay, all right, so so another student is saying we create kind of an array list, and we create like a count, and then we scan the 500 numbers of the array list for each integer in the array list. If it's equal to the value that the user has given us, we increment. Okay, so another student saying we can loop, and then we have another loop. We can loop to kind of take the input, get the input from the user, and then we have another loop that iterates through the list, and we kind of search for the size, for kind of the frequencies or the count, or essentially how many elements we have in the list. So these are solutions that are okay, not amazing solutions. So the solution is essentially, loop kind of 500 times and get the input, or not the input, essentially a user input, and then get the X value, which is the value that we want to search for, and loop through. So loop 500 times and maybe save the user input in a list, kind of an array, or maybe an array list. Doesn't really matter at that point. And then we get the value, and then we loop through the list or the array list, or array list, or even array. I mean, it's all fine. And calculate the frequency of kind of X in the list, again, or array list. So for example, let's say the user gives you numbers like 0, 1, 2, 4, 1, 2, 4, 5, 9, kind of 500 numbers. You're going to save all of that, and then when the user gives you something like 7, you're going to have to loop through all of this, and you have to see how many 7s we have. So is this a 7? Is this a 7? Is this a 7? And whenever we see a 7, we increment the counter. So okay, so that kind of works, but that's bad because each time the user gives you an X, you're going to have to go through all 500 numbers. So essentially, I mean, this is called big O of n, where n is the number of elements. So you have to do n number of comparisons, like is this 7, is this 7, is this 7, up to 500. And that's kind of slow because as n increases, as this 500 becomes 5,000, the number of if statements that you have to make will increase. So another student said, maybe we can sort the list after we're done, and maybe that'll help, but there's even a better way, a much better way than sorting or going sequentially. So kind of looking for 7, kind of one at a time. This is called kind of sequentially. So what do you guys think? Are you going to have a count for every number? So when they input a number, they're already keeping a count. Okay, that's a better idea, maybe. How can we do that? How can we have a count for every number? How can we keep the count of every number as we're taking the input, the 500 inputs from the user? All right, so Chris is saying when creating an array, the array create a variable that will auto increment if your input the value as the user inputs. Not very clear. In the loop, we just increment the counter. Also not very clear. Ervin is saying create an array for every number possible. Yeah, that's better. So someone's saying hash map. We don't want to use a data structure. I mean, we want to come up with our own kind of data structure, which could end up being a hash map or something else. So we don't want to use existing data structures except for the array. And Brett is saying we have a separate array for each number. So yeah, so Ervin and Brett, they're kind of their answers are pretty kind of close to what we should be doing. Maybe maybe it is what we should be doing, but maybe they haven't kind of explained it thoroughly. But let me tell you what I'm gathering from what I'm reading here. So the idea is we want to create a list. Now, the good thing is the numbers are between 0 and 19. So that's kind of a good thing. So maybe we should create an array of 20 elements, kind of from 0 to 19. And this can, of course, have just one column. And let's add a little bit of border here. Let's make this smaller. And let's kind of tell you what the indices are. Let me do something here. I'm gonna actually, yeah, so let's resume the sharing. So essentially that would be the index. Right now I'm starting from top to bottom just because I think that's what I have in the slides later. So let me just be consistent here. Consistent with the slides. All right, and let me make this much smaller, of course. Let me make it black. Let me remove the border. And, you know, we have, what's the size of this one? 15, let's do 15 here. And the idea, guys, is you probably are guessing right now what the algorithm is that I'm going to start with all of them zeros. And I'm going to be kind of looping 500 times, right? I'm going to loop 500 or 5,000 times. And every time I get a number from the user, I'm going to go here and increment this number. So again, the numbers that I'm going to be getting are between 0 and 19. And I'm going to be incrementing those values. So for example, the user gives me, well, let's look at what we have here. The user gives me those. So I'm going to just copy this and paste it. The user gives me 0. So that means I want to go to here and I want to get this value and increment it by 1. So that's going to be 1. Now, again, going to here or to here or to here is extremely fast. We've talked about that earlier. And because of that, when I see the value 1, I can just immediately go here and I can increment that. So that's pretty fast. I can go to 2 and increment that. I can go to 4 and increment that by 1. And then I see another 1. And when I see another 1, I'm going to go to this one and increment that. So it's going to become 2. Do you guys see what's happening? And then when the user gives me a value, say for example, how many 5s there is, I'm going to go to index 5 and I'm going to get this value, which really indicates the frequency of 5, and I'm going to just print it. So that's really some of you are kind of are answering. I mean, it seems that some of you already knew the answer. So that's the best, that's a very good algorithm. That's a very kind of good step-by-step solution to the problem that we have. And this is, again, very related to hashing, which we're gonna talk about now. I mean, all of that is necessary for you to understand hashing. Do you guys have any questions about this? And this is fast, right? Because again, when you see 2, you can immediately go here. It's easy. And when someone says, how many 5s do we have? You can go here directly. Again, that's easy. And I'm going to get this number. So all of that is very fast. So I'm not really storing the numbers. Of course, I can store them in another array if I need to. But if all that I'm asking is how many 5s and how many 3s, I really don't need to store those numbers. I can just use this array, and I can use that to store the frequencies. Does that make sense, guys? Do you have any questions about this? So, all right, let's continue. And this is these are kind of other solutions. Let me pause the sharing for a second. I don't want to go over some of the bad solutions. This is really the good solution. Essentially, create an empty list or array, loop 15 or 500 times, ask the user for the input for the number, and whenever yeah, this is the bad actually solution. This is the good solution. This is the solution that we've described. So this is kind of the bad solution where we have to loop through kind of all the elements. You can ignore this one because we've talked about this one. So that's really the fast, and you can call it clever if you want, solution. So create a list of 20 items, all zeros, loop again 15 or 500 times, and ask the user for numbers. And all you have to do is just get the current value for the value that the user has given you, increment that by 1 and update the array. And at the end, when the user asks you for, again, how many 5s or how many 3s, all you have to do is just access this array and you'll get the frequencies. We've done that, so we don't have to do an example here, but essentially you can look at this one. So at the end, you'll end up with the frequencies of those numbers. Is that good, guys? Give me a reaction. All right, let's continue. So now the question that I have for you is about names. So let's say you're asking the user for names. So it's kind of a similar problem. You're asking the user for names, and then say 15 or 500, doesn't really matter. And then you wanna, given a name, you want to get the number of the name of the number of frequencies, kind of the count of that name in your 15 or 500 names. Is that good, guys? So that's what we're trying to do. Now, if you want to do this kind of, which is what we did, and this is kind of closer to, we're getting closer to what happens really in a database query indexing, in a database indices or database querying. So to do that, what we could do is we can convert the name to kind of indices. So maybe someone gives you Ben. So Ben maybe is going to be converted to one of those indices from 0 to 19. And then we can go to that and increment. Then someone gives you Susan. You go again, convert Susan to a number between 0 and 19. That'll take you to one place. And then you increment that one. Okay, guys. Now, the question that I have for you is, how can we convert a name to a number? So you have a name, you have Jim, and how can you convert that to a number? Let's say lowercase. Let's say we want to use all lowercase. How can you convert that to a number? It doesn't have to be between 0 and 19. It can be any number. So, okay, so Alan is saying maybe we can get characters and convert them to integers. Paul is saying we can encrypt it into an int. You could, I don't think I wouldn't use the term encrypt. Maybe kind of we would encode. Encode is better. So encrypt means that we have some sort of secret. We're kind of trying to hide them. But if you want to convert that to a number, maybe you want to encode it as a number, as an integer. But how can we do that? How can we take this and make it a number? So Anna said we can make each character an integer, and that's going to be the ASCII code. Okay, so what do you do with that? So I mean, I'm going to actually get the ASCII code of those values. There's a website that I use sometimes, and essentially you would just type the letter and it'll give you the ASCII code. So A is 65, let's say J. So J is 74. Okay, so what do? You want to do 74 for J, and for I, it'll be 73. And then for M, 77, and then they're all close. Okay, so what do you do with those things, with those values? Do you want to add them? Do you want to add them up? Is that, you have to end up with just this? Okay, add them together. We can add them if you want. The problem with this the maybe rather obvious one is that you may have another name that adds up to the same result. So let's say there's this name, that name doesn't exist, but let's say this name, just by shuffling the letters, you're going to end up with 77 plus 73 plus 74. And of course, you're going to end up with the same number. Now, of course, it doesn't have to be shuffling. You can have another name, like maybe Anne will actually end up with the same result. I mean, that's possible because you're just simply adding 3 numbers and there's just so many different combinations of numbers that will give you the same result. I mean, that should be hopefully rather maybe hopefully obvious. So that's not what we would do. Okay. So Alan is saying we can actually, I like what Alan is saying, like we can concatenate them, something like that. Now this will probably work, although maybe not always. Maybe we can find a situation where, you know, this one is going to be the ASCII of a letter, and then this one's going to be the ASCII of a letter, and then this one's going to be the ASCII of a letter. I mean, maybe we can, I'm sure we can solve that problem, but it's not a bad solution. How can you get the same number? Each letter has its own amount. So Blake is saying, how can you get the same number? I mean, here we're getting the same number. These two, which could be names, they're going to give you the same number because you're adding. So 77 plus 73 plus 74 is the same thing as 74 plus 73 plus 77. So yes, each letter has the same amount. But let's say you have another one like Anne, and Anne is going to be maybe 75 plus, you know, 70, you know, say 75 plus 74. I mean, of course, this one will be 75. But the idea is A is maybe 2 values less than this, less than the M, and N is going to be 2 values more than this. So it's possible. I mean, it's possible that you have 2 different names entirely that add up to the same number. So that's possible. All right, so I'm not kind of seeing any other ideas. So let me tell you something here. And this is something that maybe you've studied in maybe discrete math, possibly. And that is, when you studied kind of binary systems and hexadecimal systems, again, you might have studied that already, maybe not, but you learn about the bases of numbers. And if I have letters from A to Z, and if I give each one kind of a value, say for example, I want to give it from 0 to 25, is that how many? We have 26 different characters. Let's say you give A0, B1, C2, like that. This one can be unique. This one can produce a unique number, different than this one, different than any other kind of string. If you do the following, if you say, I want to get the, maybe we can start from here like a number. I want to get the value of this one, C. So 0 is going to be A. Let me do some things here just to make sure that we understand. Well, let me actually, it'll take a minute, but that's okay. Let me get rid of this. So this one can be A, B, C, D, E, F. And we have kind of 0, 1, 2. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Let's do this. All right. So what you can do is you can say, if you have a name that looks like this, you can say the kind of the value of C multiplied by the base raised to the power of 0 plus the value of B multiplied by the base raised to the power of 1. Let me kind of remove some spaces here. Plus the value of C, we'll actually do CBA like that, multiplied by the base. Let me call it B raised to the power of 2. So B is for base, kind of this B. Let me call it R for radix. So R is kind of the same thing as base. So if you do that, you're going to end up with a number, and that number is going to be unique. So for example, the value of C is going to be 2. So you would say 2 multiplied by the base. The base is the number of numbers, so that's going to be 26. We have 26 different kind of shapes, and raised to the power of 0, which is actually, that's going to make this 1. So this is kind of not necessary to write this, because 26 raised to the power of 0 is 1. And here you can say the value of B, which is 1, multiplied by, again, the base 26 raised to the power of 1. So that's just going to be 26. And if you say the value of A, which is 0, yeah, I mean, that'll be actually, let me think for a second. Actually, you don't want to start with 0, you want to start with 1. So that'll be, or maybe let's give A 26. So we start with 1, we go to 25, then we give this 26, that's okay. So we can say for A 26 raised to the power of 2, 26 multiplied by the base, which is 26 raised to the power of 2. So if you do this kind of math, you're going to end up with a number, and that number is going to be unique. I mean, I can put it in Google and get the answer. So the answer is going to be this number, and that number is going to be unique. So that's kind of what we do when we have a number anyway, like a number like this, 265. The reason why this is unique and it's different than 256 is because we have 5 plus 60 plus 200. And here we have 6 plus 50 plus 200. So essentially the position of the 5 is going to indicate the value of it. And same thing here. The position of the C is going to indicate the value because we're raising the base to the position. So here, the reason why we have a 5 is because this is 5 multiplied by 10, which is the base raised to the power of 0, which is 5. And this is 6 multiplied by the base, which is 10 raised to the power of 1. So 6 multiplied by 10, we have 60. And this one is 2 multiplied by the base, which is 10 raised to the power of 2. 10 raised to the power of 2 is 100, 2 by that, 200. So this is called the positional value. It's just something that was invented many years ago. And it was invented because we can use the same symbols from 0 to 9 and be able to represent any numbers that we want. So we only have 10 symbols from 0 to 9. But for letters, we have kind of 26, and we can go from 1 to 26. And if you use the same system, which is again the value of a letter, we started from C just to kind of be consistent with how we do numbers. Kind of this one is the least significant. This one is the most significant. So this one, I decided that this one's going to be the least significant, and this one's going to be the most significant. So we start with the value of C raised to the power of, again, multiplied by the base raised to the power of 0. So that's going to be 2. Just like this 5 is 5, just like this 5 here is 5, this C is going to be just 2. And the b is going to be same thing. So it's going to be the value of b multiplied by the base raised to the power of 1. And this one is going to be the value of a, which is 26, multiplied by the base raised to the power of 2. And if you do this, you end up with a unique number. This is a unique number. So there's no other strings that have this number. It just doesn't exist. Just like there's no other number that represents 265 kind of objects, there's no other number. I mean, any other number that you write is going to be different than 265. This is a property that is true for any base. So regardless, if you use this, it'll be true regardless. You don't have to use base 10. You don't have to use R numbers. So what I'm showing you here, a system that given a string, we can come up with a unique number. That's really what I'm showing you. Now, the problem with just using this number as an index, because we can use this number as an index, and the idea is to kind of explain to you where I'm going with this, is assume that I have a huge array. So I have a huge array. I'm going to actually get rid of all of that. Oops. Let me get rid of this. So let's say I have a huge array, right? So it has many elements, thousands or millions of elements. And what I can do is I can say, when I see this ABC, I can convert that to the unique number of ABC, and I can go to that index, and I can put something here that will tell me where the row is in the table that has this as the name. So again, you can think of this as the name. Let's assume that this is Gem. And you're saying, kind of your query is select star from your table, main table, where name is equal to Gem. Okay, let's say that's what you want to do. I think it has to be like this. Well, what you could do is you can say, I'm going to actually take all the names in my database, and I'm going to convert them to a number. And then I'm going to use this number to go to a particular location. And in that location, I'm going to put the address, essentially the location of the row that has name equal to Gem. So in my database, of course, I have names, right? I have maybe students, and rows have numbers. So here, maybe I have name, and I have something here, something here, something here, and then I have Gem at some point. And the idea is, if I can get all the names, and if I can convert each name to a unique number, and if I can go to this table, and at that unique number, I can put the location of Gem, and let's kind of agree that the location is going to be the number of row. So in this case, the location is going to be 2. If I do that for all the names, I'm just going to go through all the names. For each name, I'm going to convert that to the unique number using this system. Then I'm going to create another array that's really big. Then I'm going to go to that location and put, again, the address of Gem, which happens to be the number of row. If I do that, then when I'm doing something like this, I can do the same thing, and this table will tell me where Gem is going to be, and I can go directly to Gem and get the data. Do you guys understand what I'm doing? All right. So the obvious problem is this one is going to be a huge number. I mean, if each name is going to be a number, and you have pretty much infinite number of names, then we're going to have so many different numbers. Some of them will be small, some of them will be large. So what we should do is we should take this big number, big unique number. So Anthony is saying, what if we need to expand? Yeah, exactly. Yeah, I mean, that's one problem. What if you need to expand the array? Because you might end up with a bigger number. That's kind of one problem. And even if you don't want to expand it, just by looking at a list of names and converting them to their unique numbers, you're going to end up with very high numbers using this approach. Of course, if the name is longer, like Jonathan, this one's going to be a very big number. So it's like a number. It's like a number that looks like this. It's going to be a very big number. It's going to actually be bigger than, a number that is in base 10 that has the same number of digits as Jonathan, because this is base 26. Those are base 26, which is kind of a more powerful system. By more powerful, I mean you can represent higher numbers in less number of digits. So that's kind of a problem. Another problem is, what if you want to expand it? What if there's another name that comes, which happens to have a large number, and your array, you've already created the array. So we don't typically do that. So what we do is we say, I'm going to take this number and I'm going to make it like a smaller number. I'm going to make it between 0 and 19, for example. Of course, we're not going to do 0 and 19, but let's say for simplicity, we want to do it from 0 to 19. How can we take this number and convert it to a number between 0 and 19? Can someone tell me? So you have a number that looks like this. I want to apply like a function to it. I want to put it in a function that gives me a number between 0 to 19. Let's mod it. So Anthony is saying mod it by something. Yeah, I can mod it by 20. And if I mod it by 20, it'll actually give me numbers between 0 and 19. So it really depends on what your range is. If you want to go from 0 to 19, you can just simply mod it. And here, I'm going to go back to actually this one. I'm going to steal this one. I'm going to get rid of this. And if you mod it by 20, in this case, that'll give you 4, because we have 0, 0. So this one is going to be kind of this one is this one divides evenly by 20. So if you have that, then the remainder is going to be 4. So essentially, that's what you could do. And then you would go to 4, and you can increment this one. Is that good, guys, or do we have a problem here? We do have a problem. What's the problem? What's the problem is when you see gem, or not just simply incrementing, maybe you can put the address of it, which is 2. So I can just put the address of gem, which is the second, or the row number 2. Here we start at 0. And is that a problem with this? So I'm going to take the unique number. I'm going to mod it by some other number. That means it's going to go between 0 to 19. And that number I'm going to be using to indicate where the address of gem is, or where the location of gem is. Yes, so Anthony is saying we're going to have something called collision in their structures and algorithms. And that is true. Because what I told you here is that gem is going to give us a unique number. And that's true. So let's say we have John. John is going to give us a unique number. That's true. But maybe the unique number that John is giving us is something that looks like this. And if you mod this by 20, you're going to also end up with 4. So here we have a problem. So this 4 has been mapped, or rather, these two names, Jim and John, have been mapped to the same kind of cell. And this should be kind of pretty obvious because we have thousands of names and we have 20 cells. So of course there will be collision. I mean, even if you have 100 cells here, there will be collision because you have more than 100 names. So collision is going to happen. So that's not really a problem. I mean, it's a problem, but it's not kind of an unexpected problem. It's a problem that we have to fix, but it's not something that should be kind of shocking. You have 20 elements and you have thousands of names. Of course, there will be collision. So let's see. So that's good. I'm seeing some comments. These are all good. Each index is a list of the original number before the modulo. Okay, that's good. We can do that. So what Paul is saying, maybe we shouldn't store the number 2 here, which actually tells you where gem is, because many different names can map to this one. So what we could do is we can create a list here, maybe a list or like a dictionary that has the name or the unique number. So maybe I can have Jim and I can have 4. And then for John, I would have John. And John, of course, excuse me, Jim is 2, not 4. And John is going to be here. So that's going to be 3. So I'm going to do 3 here. Do you guys see what I'm doing here? So I'm getting the name. I'm calculating the unique value. I'm modding it by a number. I'm ending up with an index number, and I'm going to go to this index number. And instead of just putting the location of Jim, I'm going to actually create this kind of simple data structure like a dictionary where I say Jim and then the location of Jim. The reason why I'm doing this is because many different names might map to the same number, and you want to make sure that you have all of them. So when John maps to the same number, you're going to say John and the location of John. So when you do kind of a select star from main table where name is Jim, I'm going to take this Jim and I'm going to convert it to the unique number. That's easy. That's just a simple equation that I'm going to use to convert Jim to its unique number, which happens to be here. And of course, I know that I'm going to mod it by 20. And when I mod it by 20, it's going to take me to 4. And I'm going to go to 4. And I'm going to say, is this Jim? And if it's not Jim, is this Jim? So I'm going to have to loop through this list. I mean, that is something that I have to do. But looping through this list, which is substantially smaller than the list of names that I have here, is much better. It's much faster. So if you don't have indexing, how is Postgres is going to do it? Postgres is going to say, is this Jim? Is this Jim? Is this Jim? And as soon as we see Jim, we're going to kind of just say, here's Jim. I'm going to get all the information from here and return it. Of course, Jim can be duplicated, but let's just not worry about that for now. But let's say we only have one Jim. We see this Jim and we say, well, here's Jim. Let me get all the information. That is extremely slow if your table is large, because Jim might not even exist in your table. So if Jim doesn't exist, you're going to have to go through all the rows, or if Jim is at the bottom of that table, you're going to have to go through all thousands or millions of rows. And then when you find Jim, you're going to retrieve, this row. However, if you have, say, 1,000, an array instead of 20, maybe we can have 1,000. And 1,000 elements. 1,000 elements is still kind of small, or maybe a few hundred elements. So if you have that, then all you have to do is convert Jim to its unique number. That takes nothing. That's just a simple operation. And then mod it by 20. That's the same operation. Doesn't really take anything. And then you have a number which is 4 or 40. It really doesn't matter. Depends on what you're modding it by, of course. But let's say you have, again, an array that has few hundreds. So you end up with, again, something like 40. You go to 40 and you have a small list of names and their locations. So you have to loop through this. That is something you have to do. But again, if you think about it for a few minutes, you will realize that this list is going to be much smaller than the list of all kind of names that you have here. Let me pause here for a few seconds and see if you have any questions. So something similar to what I'm describing here really happens. Now, of course, there are many kind of other things that we can talk about, because this is kind of a simplistic way of doing it, but the big ideas are kind of explained. So the ideas of kind of the hashing, the ideas of creating this, the ideas of kind of collision, the ideas of having a list in each element, all of those are kind of ideas that exist. One thing that I should mention here is that doing something like this is going to be, it's not going to be very smart, because if you do this, you might end up with a lot of collision, and you don't want to have a lot of collision, because if most of your names happen to be here, then you didn't really help. I mean, all of this didn't help. The best thing to do would be to have kind of an evenly distributed list. So you have a million, let's say you have a million different names, a million unique names, and you have 1,000 of elements here, then ideally each one is going to have 1,000 name. So instead of looping through the million, all you have to do is just loop through the 1,000. Okay, guys, and 1,000 is much faster than a million. Looping through 1,000 names is much faster than looping through a million names. So ideally, that's what would happen. Ideally, you would have your names kind of evenly distributed here. The problem is you can't control that exactly because there's a function here, and maybe some names will be kind of colliding. Kind of a lot of names will collide. So you can't kind of guarantee that there will be evenly distributed. That would be kind of impossible. But you can guarantee that there won't be a lot of collision. So that's something that's kind of advanced. We don't have to talk about in this course, but there are functions that are more advanced than this that will guarantee that your collision is going to be minimized. So you can essentially prove that there's an upper bound to the collision that could happen. So you can prove that the maximum number of collision that could happen is something, and that's good enough. So that's really what we want. The collision will definitely happen. There's no kind of question about that, because again, we have a million name and 1,000 elements here. So there will have to be collision, but we want to minimize the collision, and we can define the collision as having too many kind of names in one cell. So again, we will have multiple names on each cell, but we just don't want to have one cell having so many names. Ideally, we would kind of evenly distribute them. So Sweet's saying, could chaining be used to control the collision? There are many ways to kind of control collision, and again, that would be kind of a discussion for another day, probably another course. But that's okay. I mean, you don't need to know everything. You just need to. The most important part is really the big ideas of kind of how things work. That's really more important than knowing the details. So that's kind of how one type of indexing works. That's how one type of indexing work in the database, in kind of databases. Do you guys have any questions about this? We have a type of indexing called hash, and that's how it works. Again, this is a rather oversimplified way of explaining it, but that's really all that you need to know. So that I do want you to know that, of course, for the exam and the quizzes. We're gonna have one more quiz, not next Wednesday, because next Wednesday is holiday. We'll have the following Wednesday, we'll have a quiz, and then we'll have an exam. All right, do you guys have any questions about this? So here I have an example. I'll post the slides. You can look at the example. And as you can see here, we had a collision. Now, of course, Jim or Ben might exist in many, not Ben, let's look at John. So for example, we have a John here, we have a John here. So in this case, we can have a list of locations. So that could be also the case. So it doesn't have to be unique. We can have duplicates of names. And when we have duplicates of names, we want to store the list of locations. So that when you do select star from something where name is equal to John, we're gonna convert John to its unique number. We're gonna mod it by number. We're gonna end up at 4. We go here and we have a list of locations to 8. We can just simply go to 2 and go to 8 and get all the information. 8 is here because we start 0, 1, 2, 3, 4, 5, 6, 7. I think I do 1 here. I mean, based on the example, I actually start like this. So John is going to be 2 and 8. Yeah, 2 and 8. All right, guys, do you have any questions? Okay, guys, so we can end it here. I'm going to post the recordings. And again, we're not going to have a class next Wednesday, but we'll have one, we'll have one, I think it would be, what would the date be? December what? Let me see. So it would be December 1st. Yeah, so we'll have a class on December 1st, and we'll have a quiz, the last quiz on December 1st. Okay, guys, have a good rest of your day, and I will talk to you in 2 weeks. Stop recording.